Greetings, ladies and gentlemen. My name is Arderne, and I will be presenting on the work that we have recently done on the reactivity trends of cobalt-3 complexes towards various amino acids based on the properties of the amino acid alkyl chains, along with my co-authors at the University of Johannesburg in South Africa. The research in our group is focused on developing catalysts to achieve the optimum cleavage of urea. Cleavage of urea means breaking down or hydrolyzing urea into ammonia and carbon dioxide under ambient conditions. This reaction has crucial applications in fields such as agriculture, where urea is commonly used as a cheap nitrogen fertilizer. It is also employed in the fuel industry to reduce NOx emissions by ammonia reduction. Also, the carbonyl NH amide bond in urea is very similar to the peptide bond in peptides. Therefore, catalysts that can hydrolyze urea under ambient conditions might be successful in also hydrolyzing peptide bonds without damaging the actual peptide. Peptide hydrolysis has important applications in medicinal and therapeutic fields. Although hydrolysis or breakdown of urea into ammonia and other products is a very useful reaction, it suffers a serious drawback. It is not spontaneous. Urea is a very robust and stable molecule, owing its stability to resonance stabilization. The uncatalyzed hydrolysis of urea has a half-life of approximately 3.6 years and a rate constant of the order of 10 to the power minus 11. However, nature provides a solution to this problem in the form of an enzyme, urease. Urease is a nickel-dependent metallohydrolase, which catalyzes the hydrolysis of urea into ammonia and carbon dioxide. It employs a dinickel center at its active site. It is an exceptionally skilled enzyme, since it is able to catalyze the hydrolysis of urea at a rate which is approximately 10 to the power 14 faster than the uncatalyzed reaction. The aim of the present study was to develop transition metal-based functional mimics of the urease enzyme and to study their reactivity with different amino acids with varying properties such as pH, polarity, etc. The results would then be applied to understanding and identifying the sites of cleavage when applied to peptide sequencing. This presentation will be focused on the reactivity studies. We have employed cobalt-3 complexes as urease mimics in our reactions, as cobalt-3 is isoelectronic with nickel-2. The motivation behind our study is the fact that cobalt-3 complexes supported on nitrogen-rich ligands, tren and trien, have shown to catalyze the hydrolysis of the amide bond in a dipeptide, carnosine. Carnosine is a dipeptide containing histidine and alanine fragments. The reaction of the cobalt, tren or trien dichloro complexes with carnosine at a pH of 7.5 was reported to cause the cleavage of the peptide bond and the coordination of the generated histidine residue to the cobalt-3 center. Such amino acid cobalt complexes also find applications as therapeutic agents. Therefore, we decided to study the reaction of these cobalt complexes with all the 22 amino acids and isolate any products. Due to time constraints, I will be presenting the results with 4 amino acids. Coordination to the cobalt-3 metal center occurs in a bidentate fashion through the nitrogen and the oxygen atoms of the respective amino acid. There is significant hydrogen bonding as a result of this, most especially intercation hydrogen bonding that is bifurcated and even trifurcated in nature. The reactivity study was carried out for the following amino acids with varying side chains: proline, which is non-polar, asparagine, which is polar, aspartic acid, which is acidic, and histidine, which is basic. The scheme represents the reactions that were performed to synthesize the cobalt-3 amino acid complexes. The reactions were performed at pH 7.8 and a temperature of 60 degrees C. We were successful in isolating the products as diffraction quality crystals for the reactions between the cobalt-tren dichloro complex with proline, asparagine, and histidine, out of which proline and asparagine were novel complexes, and similarly for the cobalt-triene dichloro complex, we could isolate diffraction quality crystals for the reaction with proline and histidine. Both of the complexes with histidine were found to be previously reported in the Cambridge Structural Database. The cobalt-tren prolinato complex crystallizes in the monoclinic chiral space group of P21. The asymmetric unit of the unit cell contains a cobalt-3 amino acidate cation supported by 2 iodide anions and a water molecule of crystallization. As previously mentioned, the cobalt-3 center is coordinated to the 4 nitrogen atoms of the tetradentate tren ligand and the pyrrolidone amine nitrogen and carboxylate oxygen atoms of proline in a bidentate chelating fashion, non-planar, inevitably permitting a distorted octahedral geometry. During the refinement of the crystal structure, it was found that one of the iodide counterions exhibited positional disorder, and a suitable disorder model was used to further refine the structure. The crystal packing network of the cobalt-tren prolinato complex shows bifurcated intercationic hydrogen bonding, as is evidenced over here, between the 2 cations. So this is the first cation, this is the second cation, thereby threading cations down the B-axis in a zigzag head-to-tail fashion. Highlighted hydrogen bonding data are summarized in the table on the slide. There are 2 unusually long hydrogen acceptor bonds, which are most likely indicative of relatively weak charge-assisted packing stabilization interactions between the cobalt-3 cation and the iodide anions. The type of packing can be described as helical threading of cations and column stacking of cations along the B-axis. The graph set analyses reveal a variety of direct, chain, and ring motifs, where one ring motif is being highlighted here. The cobalt-tren asparaginato complex crystallizes in the monoclinic space group P21/N. The asymmetric unit of the unit cell contains a cobalt-3 amino acidate cation supported by a chloride and a perchlorate anion. In the molecular structure, the cobalt-3 center is coordinated to the 4 nitrogen atoms of the tetradentate tren ligand and the amine and carboxylate atoms of the asparagine in a bidentate chelating fashion, inevitably permitting a distorted octahedral geometry, similar to the previous complex shown. During the refinement of the crystal structure, atom C7 was calculated to exhibit S-chirality, despite the molecule crystallizing in a centrosymmetric space group, and all other aspects of the refinement were routine. The crystal packing network of the cobalt-tren asparaginato complex stabilizes the structure by utilizing 2 types of hydrogen bonding moieties, that is, charge-assisted and intercationic intermolecular hydrogen bonding in the form of NHO interactions of the carboxylic acid from asparagine oxyanion from the perchlorate, and primary amine of the tren functional groups as building blocks for infinite arrays of head-to-tail threading, head-to-head threading, and ring motifs. Highlighted hydrogen bonding interactions are summarized in the table. There are 3 unusually long hydrogen acceptor hydrogen bonds calculated during the refinement, which are most likely indicative of relatively weak charge-assisted packing stabilizing interactions between the cobalt-3 cation and the perchlorate anion. The type of packing can be described as spiral or helical conformations along the C-axis and the interlocking of multiple complexes to form a wave-like packing arrangement along the B-axis. The graph set analyses reveal a variety of direct chain, ring, and self motifs, the most obviously visible being the C7 motif. The cobalt tri-N prolinato complex crystallizes in the orthorhombic space group PBCA. The asymmetric unit of the unit cell contains a cobalt-3 amino acidate cation supported by a chloride and a perchlorate anion. In the molecular structure, the cobalt-3 center is coordinated to the 4 nitrogen atoms of the tetradentate tri-N ligand, and the pyrrolidone amine nitrogen and carboxylate oxygen atoms of proline in a bidentate chelating fashion, which is non-planar, inevitably permitting an overall distorted octahedral geometry. During the refinement, atoms N4 and N5 were calculated to exhibit S-chirality despite the molecule crystallizing in a centrosymmetric space group, and all other aspects of the refinement were routine. The crystal packing network of the cobalt tri-N prolinato complex utilizes 2 types of hydrogen bonding motifs, that is, charge-assisted and intercationic intermolecular hydrogen bonds involving carboxylic acid from the proline, oxyanion from the perchlorate, and the chloride anion and primary amine of the tri-N functional groups, and introduces a helical threading head-to-tail conformation with the chloride linking the columns in between. Highlighted hydrogen bonding interactions are summarized in the table. There are also 2 unusually long hydrogen acceptor hydrogen bonds, which are most likely indicative of relatively weak charge-assisted packing stabilization interactions between the cobalt-3 cation and the perchlorate anion. The type of packing can be described as grid-like along the A-axis, stacking and threading in a zigzag-like conformation along the B-axis. The graph set analyses reveal a variety of direct chain and ring motifs, the most obviously visible being the C7 motif. This slide shows the UV visible spectra for the reactants and the products. The spectra differ considerably from one another, and almost all the amino acid data complexes experience a hypsochromic shift as compared to the cobalt tren or tri-N dichloro complexes. Since all the amino acidate complexes possess a fairly strong absorption band at 345 nanometers, the reactions were followed spectroscopically by monitoring the increase in absorbance at 345 nanometers. The reason we chose this absorbance value was because the absorbance at 475 nanometers does not increase significantly enough for us to allow reaction monitoring, while this was the case for the peaks at 345 nanometers. Over a 2-hour time span, a 1.5 microliter aliquot was taken out of the reaction vessel every 20 minutes, and the reaction was quenched in 1 milliliter of iced deionized water. Thereafter, the aliquots were analyzed by monitoring their increase in absorbance. This is a short video showing the reaction mixture with a color change from deep pink-red to the orange-red final complex. On this slide here, we present the spectral changes for the reaction between the cobalt triene dichlorocomplex with histidine. The comparative spectra on the right indicates the formation of the cobalt triene histidinato complexes in solution. This slide shows the spectral changes and the aliquots withdrawn and analyzed for the reaction between asparagine with cobalt triene or tren dichloro. Some reactions had a gradual color change as evidenced on the top photograph, whereas for the other reactions the change was fast and immediate. Here we present the summary of the reactivity studies for the 4 amino acids. Most of the reactions proceed with a positive slope. However, highest initial rates were observed for the alkaline amino acid histidine with both the tren and triene complexes. Since we explored the reactivity of the cobalt, tren, and triene complexes with different amino acids, we decided to also analyze their toxicity towards healthy cells. The toxicity profiling was carried out on WS1 fibroblast cells, and the cell viability was monitored using the trypan blue viability test and by analyzing the cell morphology by inverted microscopy. What can be seen here on this slide is the cell morphology images taken by inverted microscopy after 24 hours of incubation. Careful examination of the cells showed that they remained healthy even up to a relatively high concentration of 25 millimolar. In conclusion, the reactivity of the cobalt-3 dichlorocomplexes towards various amino acids was explored using single crystal X-ray diffraction and UV visible spectroscopy. The complexes were found to have a stronger affinity for the alkaline and polar amino acids, probably due to the possibility of coordination to the metal center and formation of amino acidato complexes. The reactivity trend observed was found to be L-histidine, basic, followed by L-aspartic acid, followed by L-asparagine, which is polar, followed by L-proline, which is non-polar. The complexes were found to be completely non-toxic towards healthy cells, even up to 25 millimolar concentrations. This work has recently been published in the International Union of Crystallography journal, Acta Crystallographica, Section C, Structural Chemistry. We would like to acknowledge the following centers, institutions, and funding agencies for allowing this work to be carried out. And lastly, we'd like to thank you for your attention, and we welcome any questions or comments you may have.